Okay, so we're gonna go over quiz number 6. Let me go ahead and start sharing. All right, quiz number 6. Let me just get this one out the way. Minimize it. Okay, quiz number 6. Okay, so this one just asks you for the basic concept. Which of these Butterworth curves have a slope approximately minus 60 dB per decade in a stop band? Okay, so anything in the first order that would be represent one pole filter that would be minus 20. So the two order would be 2 times 20 would be negative 40, and then the third order would be 3 times 20 would be negative 60 dB. So 60 dB here. So the answer is be the third order. Okay, so the answer is C as in cat for number 1. Okay, any question on number 1? Okay, no question. Next set. Okay, the third order filter is also called A. So the answer is D. So D as in David, 3-pole filter. So the third order is same thing as 3-pole filter. So the answer is D as in David for number 2. Okay, any question number 2?
Hi, Sam, it's me, Luis. I got a question. I thought it would be C.
Why it's C? You got first order, second.
Turn on your microphone.
Yeah, so you got the so you got a first order, second order, third order. Okay, according to this picture right here.
Got it. I see it.
Okay. And so that's what it is. The third order represents a 3-pole filter. We don't know whether it's Butterworth filter, Bessel's, or JFET, because I remember when you look at the, I don't think I have that schematic for JFET. And so you're going, so this is would be like JFET, okay? So none of those would represent any, it doesn't look like Butterworth, doesn't look like Bessel, it doesn't look like JFET. So that's why, so you have same color combination, but it doesn't look like a JFET or Bessel or Butterworth, okay? So, but it's called by the order. So first order, second order, third order. Third order is the same thing as the 3-pole filter.
I got it. I understand it now.
Okay, very good. Okay, next set. Okay, number 3, a low pass filter. Okay, so you for the low pass filter, ideally it has no gain in the stop band. So anything right here at the cutoff, there should be no gain at the cutoff here. It should be going, the voltage should go to 0. Okay, ideally from here it drop down to 0 automatically. So ideally this is what we want, is ideal situation. So attenuate frequency in the stop band. So as you can see, so the signal is being attenuated as keep on dropping until to the point that goes 0. Okay, and and it has a maximum gain at minus 3 dB. So all your maximum gain is all the way up to the 3 dB. Anything below that, it's going to be cut off or it's going to be stopped. And so you want to attenuate that signal. Okay, so your maximum gain is within the minus anything above the minus 3 dB. So the answer is D as in David for number 3. Okay, number 4, the phase shift of a two-pole low-pass filter is, okay, the answer is C as in cat, greater than of 1-pole filter, okay? So that, like I said, most of the time you're gonna find the information is on Google, and this is what so this is the website that I did a research on it, and just to give you a little bit more information, if you wanna go through and read it, that's fine. You go to this website. Okay, and this right here, you got phase response of single pole filter. Okay, so therefore in the middle it's going to be at 45. So from here to here it's got, so total together is 90 degree. Okay, so you got a 45, so 45 on top, 45. So you got the low pass would be this here from 0 to 90 degree. Okay, and this one said phase response of a two-pole low pass filter is going 0 to 180 degree. Okay, so therefore the phase shift is going to be increased the more as more poles is added onto the circuit. Okay, so that was answer for number 4. So the answer is C, greater than that of one pole filter. So any question number 3 or 4? Okay, no question. Next set. Okay, so number 5, which filter has the sharpest roll off? Okay, so roll off is after the after the cutoff frequency, which is right here. So the one that is closest to the ideal is this red one. So this red one is cut off right here. This is your roll off, and that is called the JFET. So the answer is C, as in cat for number 5. Okay, any question on number 5? Okay, no question. Okay, number 6. Okay, based on these curves, is the advantage of JFET filter over the other is mainly the most of the advantage is mainly the roll off or the stop band response right here, because it's going close, moving close to the ideal. So this is the best one, you see. That's the roll off or the stop response. Okay, it cannot be pass band because pass band there's a whole bunch of noise here, so it's a whole bunch of ripple, so that's not its advantage. That will be disadvantage. And transient response, well, you can see it's a, you know, this response is kind of vary all the way through, so it's not that. So the answer is B as in Bob for number 6. Okay, any question on number 6? Okay, next set. Number 7, if a low pass filter has a 1 volt peak to peak sine wave input and a pass band gain of 10, its output voltage of FC would be, okay. So we know the gain is going to be 10, okay, and then V in is going to be 1 volt peak to peak, okay. So the maximum output that can be possible is gain times the V in, so that's coming 10 times 1 volt peak to peak. That will give you a maximum of 10 volt peak to peak, okay. So V out at cutoff is going to be the 0.707 times V out max, okay. So therefore 0.7 times 10 volt peak to peak, which equal to 7.07 volt peak to peak. So the answer is B as in Bob for number 7. Okay, number 8, which response curve represent a practical high pass filter? Okay, so practical high pass filter would be this one. The answer is B as in Bob for number 8. Okay, any question on number 7 or 8? Okay, no question. Next set. Okay, question number 9. An ideal high pass filter has, okay, so it has an infinite dB per decade slope in the, it should be say stop band. Okay, so anything right here is your stop band where you got no signal at all. It's supposed to be stopped. So, so you got so infinite dB per decade slope in the stop band. A flat pass band response. So you got pass band right here, pass band straight flat. And no high cutoff frequency. So we don't know what the cutoff is. Look like a continuum, look like the arrows keep on pointing that way. So just keep on going. So the answer is D as in David for number 9. Okay, any question on number 9? Okay, all right, number 10. Okay, a proper way to lift a heavy object is mainly to make sure you bend your knees, grasp the object, raise yourself, and the object by straightening your legs. So the answer is A. Okay, so we don't want to bend our back. We don't want to bend at our waist because that would, if anything goes wrong, then you're going to throw out your waist. So you can use your knee. That's the best ideal. So the answer is A as an apple for number 10. Number 11, term used to describe opposition to current flow is resistant. Okay, so resistant is so you got R here. So the R would reduce your current. Or if you're less resistant, you're gonna have more current. So the answer is mainly C as in cat for number 11. Okay, any question number 10 or 11? Okay, next. Okay, number 12, the opposite of resistant is conductant. So the answer is C as in cat for number 12. Number 13, another term for electromotive force is voltage, A as an apple for number 13. Okay, any question number 12 or 13? Okay, no question, next set. Okay, the unit of measurement of electron flow is, so when you measure electron flow, you mainly measure the current or the ampere. So the I is the current. So the answer is D as in David. Okay, so for number 14, D as in David. Okay, any question number 14? Okay, no question. Okay, so everyone did pretty well on this quiz. We got a couple of people did not turn in one, so now it's a little bit too late. So, okay, so if you did not understand this one, make sure you go through the quiz and make sure you study for this one, okay?
You go
All right,
back number 5, please.
Excuse me?
Could you go back number 5, please?
Okay, hold on one second.
Thank you.
Okay. So number 5 would be here, okay?
Okay. Number 6.
Okay, which filter has the sharpest roll off? Sharpest roll off is right here, which is right here. So this one is the closest to the ideal. So that's the sharpest. So C is the chef, the red one. Okay, number 6. So the best, so for the chef, so chef is a red one. It cannot be in the passband because there's a whole bunch of noise or ripple here. That is the unwanted noise in your circuit. But it has the best roll off because it's the best that is close to the ideal at the stop band. It's closest to the ideal circuit.
Okay,
So the
thank
answer
you.
is B as in okay, you're welcome. Okay, any other question? Okay, so that's pretty much it. Back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Okay, so hello everyone. Okay, we get the quiz. Let's just try to very basic review. We'll be helping you to memorize when you get the job interview. Okay, week by week, we keep doing over and over until you see the question you can answer right away without any more information needed. So the lecture on the Zoom is much better in the classroom. Okay, we can give you more things to do and keep over and can help you understand. The thing is, sometimes you go through only one time. First thing, I don't believe you can understand. The second thing, after you understand, I see you can memorize it. Okay, so I have to be few times. That will be help. If you get a job interview and you want to review what you want to review, too many things. Okay. So make sure if you want to complete the program, try to do your lab. Okay, just a minute, okay?
Well, some medication from the pharmacy. Why?
Yeah. Okay, thank you, sir.
Welcome. Can I get a signature?
Disappear.
Yeah.
Yes. Good evening.
Good, good. Okay, so anyway, last time we already go with the JFET amplifier. And now just wait for me to convert it into my iPad. Okay, quickly go to review last time. Basically, you need to amplify the signal, like your voice. We can get either bipolar transistor or JFET transistor as an amplifier. Bipolar, you get a CB amplifier. JFET, we get a common source, common drain, and common gate. They almost the same, okay? Only thing is, they want you using the JFET amplifier. The thing is, JFET get a very high input impedance. However, if you want more gain, then you better using bipolar transistor. Okay? And again, this try to helping you if you want to converting a DC circuitry to AC for analysis. Then you get the 4 steps. First thing, set on the DC source to 0 and replace by the short circuit. Number 2, replace on capacitor by short circuit. So that's why in the AC circuitry, you cannot see any DC power supply. And also no more capacitor. The thing is, DC power supply short to ground, and capacitor will be shorted, just like the wire. Number 3, remove all elements by part by the short circuit. Okay, redraw the network in a more convenient and logical form. What that means? This will be telling you this is the DC, okay, analogy for N channel and the P channel. However, when you're converting into the AC equivalent, then this is the gate here, this is the short, and this is the drain. Okay, only the drain go into the source to get the current source. Okay, and they will be equal to Gm times VGN. This is the internal resistance output of the JFET. Basically, this resistor is too big, so that's why most of the application we ignore. We don't care. That's small RD. Okay. FET input impedance equal they want infinity O. FET output impedance. Okay, they will be 0 equal R small d based on this display here. You don't have anything else. So that's why they get only this resistance. Okay. Okay. And this is a component of an admittance equivalent. Okay. They will get the range 10 to 50 microsiemens. Now, when you're looking into the circuitry, first thing, you must be recognize what the JFET amplifier. You get common source, common drain, common gate. And this is what we call a common source. In order to recognize input applied to the gate, output will be coming from the drain. That will be common source. Okay. Also, they're telling you input, output will be our phase. That means input positive, output negative. Input negative, output positive. They will be 180 degrees of phase. That is the first thing you need to recognize. Second thing, when they build the amplifier, they must be using the DC bias circuitry. So by looking into the circuitry amplifier here, and you have to know what type of the DC bias. And we know we get a negative voltage here, so we know they will be a fixed bias. Okay? And basically you supposed to know or not the minimum calculation for the DC bias. Okay. Also, try to make sure you understand the voltage VGG and the VG, they will be the same. If you get a minus 2 volt here, and VG also minus 2 volt here. Okay, how? The thing is, you get a resistor RG here. The value very high. So that's why the current cannot flow in here. So the voltage here and the voltage here will be the same. If you want to take that out, just connect directly to the VGG. That's okay. However, we cannot do that way. Will be explained to you on the next one here. Okay. Okay, let's see this one first. Now, if you don't have a resistor RG here, just connect directly. So when you get apply the sideways, right here, they supposed to get a sideways. However, for AC, VGG short to route. So that sideways will be go to the route. They cannot go to the gate. Okay. If you get a big resistance here, so that will be allowed. Sideways, go through the C1, and then they can go to the gate. Okay. And input impedance, that means from the input V in, look into the JFET, that's what the input impedance. And from the output here, look into the JFET, that's what they call output impedance. Now, this is given you a little more detail V in here. Okay, capacitor shorted. Okay, this is the VGG shorted, so that's why they connect to the route. Okay, if you don't have a this resistor here, the sideways go this way, they can be short to the route. They cannot go to the gate. So that's why you must get this resistor. Okay, the dark part in here, that is internal of the JFET. Okay, on it, so you can see this is the gate, this is the drain, this is the source, and between the drain to the source, you get the current source, the value GMVGF. Okay, and now if you get the RD, that means the drain resistance, then they will be VDD short to the route. So GL now, if you're looking into the amplifier, you see only a big D, not one will be a small d here. We ignore that. We take it out. Okay. And also, if you're looking input impedance to the JFET, you can see this is the big resistance here. And also, they explain to you right here. GL supposed to be R big D parallel with R small d in here, okay? But that they say not practical. Common short amplifier again, okay? So now this is the gate, this is the input here, right here will be the source, okay? This is the source, okay? So basically from the drain, again, go to the source to get the current source. And also from the drain, you can get the resistance R big D. So if you want to see input impedance, you're looking this way. You see that one. Okay. So if you're looking output impedance, you're looking from outside to the output here, you can get only one resistor in this case. Okay, so if you want to see calculate the gain, okay, the gain AV equal V out divided to VE. V out equal minus this current here time big resistance RD. The minus sign just telling you input, output will be off phase. Okay, and the VGS, that means from a G to the S here, VGS, okay, equal V in. That means the V in right here. And that will be VGS equal V in, okay? Then V out equal V AV, that means minus GM VGS time with RD. So AV will be equal V out divided V in. So basically equal minus GM time R big D. If the load include, then otherwise if the circuitry get the RL, the load, so the output impedance have to be R big D parallel with R big L. Okay. This is last time we already done. Okay. I just quickly go through. Okay. They given you the circuit, and they already given to you VGSQ and IDQ. So that means you don't have to do any calculation for DC. Okay. And they want to determine the GM. We already telling you GM equal GM0 times 1 minus VGS over VGS off. What is GM0? Okay, that means GM0 is the value at VGS equal 0. Normally, data of the JFET will be given you value of GM0. If it's not, you can calculate the GM0 by 2 times IDSS divide absolute value of the VGS off. The thing is you cannot get negative for GM0. Okay? And they want to calculate the input impedance. You get that guy here. Okay? Output impedance, in this case, no load, then they will be equal R big D 2K. Okay? And they want AV. Okay? And AV, you already know the formula from a previous here. AV. Okay? GM time RD. And I given you answer will be 3.75. Okay? So this is more detail what we are already talking about. We don't care on this guy. Okay? And this will be R D V in L. Okay? Common short again. This is the thing you need to know. Signal applied to the gate, output from the drain. And if you get a sideway here, and if you get a sideway at the gate, if you don't have a resistor here, they short it to the route, then this sideway will be go to the route. Okay? So that's why we have to get this resistor. And this is a bypass capacitor. Bypass RF. Okay? So if you measure at this short, you can get the voltage DC, but not the AC. The thing is they shorted to the route. And the output from the drain, you see that they will be 180 degrees out of phase. Positive, you get negative, negative, you get positive. Okay? And this capacitor here will be DC block. or AC coupling. That means they just like the wire. They only allow this signal go to the output, but not the drain DC voltage can be go. Okay, so that explains everything on this circuitry for common source. Normally you will be see. If I can see the output impedance, there will be this resistor and this resistor in parallel. In this case, we get a load, 10 kilo ohm. Okay. Now, if you're looking on this circuitry for common source, what the DC bias circuitry will be using? You understand, for DC bias, you get a curve. Let's see, fixed bias, cell bias, voltage divider bias. So on this one here, okay, at the gate, you don't have any voltage here. Okay, so they will be cell bias. And before you're doing a calculation for the amplifier, you have to go to do the calculation for DC bias first. Okay, and for the cell bias, if you want to do a calculation for the DC bias, you need the graphic. That's what they don't want it. So on this circuitry, they gave it to you 1 volt at the source right here. So that's given you easy to do calculate for the IS. Okay, 1 volt here, around here, 200 ohm here. IS will be 1 volt divided 200 ohm. You get the IS. And we already said in the JFET ID and IS all the time will be the same. So you get the IS, that means you get the ID here. Okay, and that will be helping you. Also, you need to calculate the VGS or anything else for DC, need for the amplifier. Okay, so now this just a very summarize. Input impedance, RG. Output impedance, you get RD only. Parallel with internal here, but we don't want internal. Okay, so that's why in this case, output impedance equal only big D. Okay, they put in here, that means they say if RD greater than equal 10 times half big D, so ignore that. Okay, so basically that I get the document from one of the university. Summarize for the common source. AV, that means the voltage gain equal minus GM times RD. We don't care about R small d. Okay. Phase relation. Common source amplifier configuration has the 180-degree phase shift between input and the output. Okay, that is what need to calculation. We already your guy have to do it. Okay. Okay, on this one here, Let's see. Can you quickly go to get the answer for me in A, B, C, D, E, F, G, H, I. Okay, so make sure we can have some student couldn't get through right now. They're able to see later and try to get the value. But however, this will be sell buyer. Okay. However, you don't have any graphic. That's why they given to you. ID equal 1.95 milliamp. VGSQ. That means VGSQ, what VGSQ equal? I given you the formula. Maybe I still memorize. V G minus VS. VG right here equal 0. VS will be ID times RS minus, okay, ID times RS. So you know how to do calculation. Okay, and VD this is the D right here. This will be the S. VD equal VDD minus ID times RD. Okay. VS equal ID times RF. GM0. I believe they will be 2 times IDSS. Divide absolute value VGS of. Okay. And GM0 equal GM. Now, GM equal GM0 time is it 1 minus? Let's see.
Yes. 1 minus VGS divided by VGS off.
Okay. 1 minus VGS divide VGS off, right?
Yes.
Okay. G in you can see equal 10 mega, 1 mega over 10 mega ohm. GM0. GM0 will be equal R big D. The thing is no load resistance. Voltage gain. Let's see, looking voltage gain. Minus GM times RD. V out AV time V in. Okay, so that is including on of the formula for you to do your calculation. I wish you can type the way like myself. Even you don't have to do calculation, you still can get the formula, how to do calculating. Okay, so any question on this example? Okay, if it's not, common drain, second one. We try to go through on of the amplifier for today. This is a common drain. Now, first thing talking about the circuitry, what DC bias. And now you can see, you get a no VGG here. That will be cell bias. And without the graphic, if you want to do calculation, they have to give you some value. Okay, so you can calculate the DC bias. And if I'm looking into the circuitry, input applied to the gate, output now from the source, that is the output. That's what we call common drain. Okay. Okay, so basically you get the gate here, you get the drain, and you get the source here. You get the current from drain to the source. GMVGS. We don't care about this guy here. Okay. And this is G out. And this is G in. If you look the G out, that means you're looking this way. You can see this resistor right here. Okay. And input impedance RG here. Okay. And they given you the formula. Now, G in equal RG. Okay, easy. G out. Basically, you will be using this formula. Not this one. The thing is, we ignore internal output resistance as small d. Okay. And also, you want to calculate the AV, the gain. This is the formula we'll be using. Not that one. The thing on that one, they're using also including output impedance small d. Okay. That is not practical how to do it. So when you're looking into the common drain, try to recognize this is a common drain. And you get the input impedance, you get the output impedance, you get the gate, voltage gain. Vout will be equal gain time input. Okay. Now let's see. Common drain amplifier. So basically, they just try to give it to you. Okay. I summarize in here. Gout for the network. Okay. Let's see. This is the Gout here. Okay. This is input VGS. That's the voltage from the gate to the source. Okay. And basically, that's what they're telling you. If you want to calculate the Gout, okay, they will be RS parallel with 1 over GM. Okay. And we don't care on that one. We ignore R small d. Okay. And also, if you want to calculate the gain, then AV equal V out divide V in. GM times RS divide 1 plus GM VS, you don't care on that one. That including R small d. If you want it, you go to the University for Engineering, then you have to know. Okay? They want including R small d. But if R small d higher than 10 times of RS, that means they will be ignored. Normally that output internal resistance get a very high value. Okay. So now, in this circuitry here, example for the drain, a DC analysis of the short follower will result in VGSQ 2.86 volt and IDQ 4.56. Okay, so basically that's a cell bias. You need a graphic, but they don't give a graphic, so that's why they given you the value here. That's DC ID. Okay. And also VGSQ. So you don't have to do calculation for that DC. And they want to know what the value of GM0. The value of the GM. We already know the formula. Okay. And they get the input impedance. In this case, you will be at 1 mega ohm. Okay. Output impedance. If you look in this way, you're able to get output impedance and the gain. So that will be telling you everything here. Okay. Output impedance, okay, will be equal RS parallel with 1 over GM. Okay. So output impedance will be equal RS parallel with 1 over GM. And they want the gain, okay, will be GM times RS. Okay, divide 1 plus GMRS. Okay, so that only two formula. I give it to you, GM0 or GM. We already did calculation before. Okay, that you must think. The thing is basically, they don't want to ask any question, go into too much detail. Okay, and this is the common drain here. And also they're using cell bias, so that's why they given you VS here. If you get a VS, you can calculate the ID. ID IS equal. You take VS divide RS, you get the IS. Okay. That will be helping you to solve that problem. Okay. And now in here, they do the calculation, everything. I hope you can get through this thing. Okay. Every formula we already gave it to you. In here, they just try to make sure, okay, you know GM0 minus VGS over VGS off. And also, we want to calculate the gain. They will be equal to GM times RS divide 1 plus GM RS. The last one, common get. Let's see. This is the gate. Okay. This is the drain. And this is the source. Okay. Common gate input applied to the source. And gate will be rounded. This will be round. And the output from the drain. So basically, when you say the input applied to the source and the output from the drain, that will be common gate. Okay. Common gate input output will be also in phase. Common drain input output will be in phase. Only the common source input output will be out of phase. Okay. And this is just showing you internal of the JFET. Okay. Right here, internal right here. You get the source, you get the drain. Okay. Basically, the drain go to the source to get that GM VGS current. And this will be look like input impedance. And that will be look like output impedance. Go to the drain. Okay. So they give it to you input impedance. In this case, they will be equal RS in parallel with 1 over GM. Okay. Output impedance. This way, you get R big D. And the gain will be equal GM times R big D. Common gate configuration has no phase shift between input and the output. Okay, so this example will give the common gate. Okay, on this one, they already given to you VGSQ minus 2.2 volt and IDQ 2.03 milliamp. So that's why you don't need the graphic in order to calculate for DC. And what they want to calculate the GM0. You already know GM0, okay? Equal, I think 2 times IDSS divide absolute value, FVGS off. And number B, GM equal GM0 times 1 minus VGS over VGS off. And they want to calculate the input impedance. Okay, input impedance, we gave it to you right here. Okay, RS parallel 1 over GM. Output impedance, G out, they will be equal R big D. Okay. Output impedance equal R big D parallel with RL if you get the output load resistance. Okay. If you don't have it, then they just using RD. The gain AV equal GM times R big D in this example. Okay, you want V out. V out is going to be in time the gain. Okay, also will be let you know if I asking any calculation, I will be given to you the formula. Only thing is you know how to do calculation. Okay, the thing is it's hard for everyone to memorize on of the formula, even myself too. Okay, and on this one here, you can see the different need. They get the load for 15 kilo ohm. So they want to do calculation IDQ, VGSQ. However, they given you the value right here. Okay, so basically this is a common gate. So that will be G right here. Okay, S right here. And that will be drain. Okay. So also we already gave it to you. If you want to calculate the input impedance, RS parallel 1 over GM. If you want to calculate the output impedance, now they could be R big D parallel with RL. Okay. And if you want to calculate the gain, then there will be a GM time output impedance. That means time RD parallel with RL. And finally, you want to calculate the gain and the V out. V out will be equal V in time the gain. Okay, so basically that will be done for JFET amplifier. Okay, we should try to go over and review, do example, make sure you know how to working on JFET amplifier. Okay, so basically you must be remember to get 2 different type transistor, bipolar, NPN, PNP, and JFET. They commonly is the same thing. That means if you want to make a amplifier, Then bipolar, you get CE amplifier, CC amplifier, CB amplifier. On the JFET, you get a common short, common drain, common gate. Only thing you make sure you memorize for CE amplifier, you get a good gain. Input, output, 180 degree of phase. JFET have a not much gain. The benefit is they get a very high input impedance. That only thing. For common source, input output the same like CE amplifier. Input output 180 degrees of phase. On the other one, they don't have much gain. Input output will be in phase. Okay. So, any question about the JFET amplifier? If it's not now, make sure everyone try to understand for me. If you want me to help you, don't, especially for the texture on the D lab, don't send your test program to me asking for to see which one is wrong. No, I cannot go to the line by line or test by test to see right or wrong. No, cannot have enough time. What I can do, just text to me you want to be on Zoom. And that's why if you say, okay, you fail on test number 4, then I can help you out. I can look into the test number 4, why it failed, then helping you to get it that very quickly to get it done just few minutes, not much. Okay, so any question, anything, either 1 or 2. Make sure take 2. You already go through on of the lecture. Only thing we just want you to complete your lab, either lab 4 or the D lab. Okay, will be summarized for all of the students to see what lab 1 you already done so far, or what the D lab. Okay, that is helping me to decide to given the complete certificate in this program. Make sure you try to be in the lab to do the lab, okay? Especially on lab 4. On the other lab, software you can do at home. You can build the circuitry at home, okay? That can save the time. However, you want to test, you have to be in the class using the control box. If you're not doing it, that will be delay the time you want to complete the program. Just about few weeks, will be let you know. 8 students in the program, what your status on the lab 4 and the status on the D lab. Okay. Any question? Okay, if it's not, yeah, go ahead.
I apologize for that. That was me that you were talking about, sending that thing like that. Because I think the number 21 failed on 11.
Okay, you want it, you can go ahead and share.
Okay, hold on just a second.
I stop share on this one.
Okay, just a second. Just a minute, just a minute, just a minute. I'm rebooting, Mr. Pham. It'll be coming up in just a second here. Hold on.
Yeah, that's okay. No hurry.
Okay, hurry up. Okay, so come back here. And we do share screen. And we do. Can you guys out there see it?
Not yet.
Black screen.
Okay,
Yes.
now okay.
You can see it?
Yeah,
Okay, so
what that fell.
it was a 21. So, but I think it's down in not 6, 3, 4, 5. Because my box is intermittent, so I can't really use it. But tell me where you want me to stop, Mr. Pham. Because I
want to know that file will be on ADC data, right?
okay, so well, let me go down to where the function definition is at. Okay, let's pass here.
That is the one.
Okay, wait a minute, hold on. Okay, right in this area. I copy paste like you said, but
Yeah, it look like to me it okay. Go a little up.
up or down?
Up.
Up, okay.
No, down. Sorry. Okay, hold on. Okay, to say that write address to memory, yeah. Expected data equal ADC data per se. Read memory. I didn't see anything wrong in the loop.
Mm-hmm.
Okay, so it didn't make sense to me when you say fell in the middle, right?
Yeah, because it went down the last week. We on Friday. It went down to I think it's number 20 and stop.
Yeah, that didn't make sense to me. Either you can hit into two problems. the control box. That's the one. Second thing, you can get the memory IC.
Mm-hmm.
So you when you do the lab in the class, you can using one box control box at the.
Yeah, I know what you mean. Try switching out different control boxes.
Exactly.
And then if that don't work, maybe switch out the memory.
Exactly. Then that I see.
Mhm. Hey, Sam, I know you there. You got pretty sharp eyes too. Did you notice anything?
You have to go back into the top testing. You have to go.
Okay.
Okay,
I'm gonna go down
down.
real slow and let me know.
Go look at test 3 and 4. Go look at test 1, 2, 3, and 4.
Okay, yeah, here's one.
Okay,
coming
so
up now.
1 is going to enable U3. Okay, so that was testing. That's number 1. Test 2, go down to test 3.
Here's test 2.
That
Go
three.
down, go see
Test
that.
3 is coming up right now.
Okay.
Test 3, you didn't do anything. Test 3, you did exactly the same thing as test 1. So test 3 is wrong.
Well, no, I passed this.
Test 3 is wrong because you're doing exactly the same thing as test 1. You serialize the data and you enable U3 and then you verify the data. You didn't go through, you didn't go to
Exactly.
U6, U7. They've never gone through U6, U7.
So what's wrong with 3?
You didn't see, look at your test title. It's supposed to go through U6, U7, right?
Right.
Where is your, I'm looking at your program. I say serialize the data and then enable U3. And no, I never seen it go to U6 or I never seen going through U7.
Oh, so you're saying that I gotta put in the part, wait a minute, hold on. I gotta put in the part up here, which is enable U6, enable U7.
Now, that U6, U7. Number 38.
Number line 38.
Right.
So
You
line
go on that-
38.
You just go on that function.
Okay, okay, so right here,
Right. Go on that function.
call this function.
Enter data 0x55.
Okay, control C. Okay. So now I
And
okay,
go up there.
go back to 3
Yeah, exactly.
and then come after.
Expect data 55 correct. Pcop correct. But delete 147.
Okay. Okay, let me
155.
do what now?
Delete line 147 to
One-
155.
Okay, line 147. I mean, 147 is right here.
Right, delete that.
Okay, wait a minute. I can just do this. And what else?
Up until 155.
Up until 155. Okay, so I can actually do this then. I can do this. Wait a minute, hold on, wait, excuse me. That, and then I'm gonna come back up here and do that and that.
Correct.
And now that the part,
After 146,
that's why I paste.
yeah, pet them out. That U6, U7.
Right. Okay.
That's it. But the data, integer data, you have to say 0x55. Not integer. Change that to 0x55, everything.
And then delete all of that.
Yeah. That means you passing 0x55. That's it. And then when you go into step number 4,
Okay, test number 4.
Okay. After the line 162, after that line,
Mm-hmm.
adding the same line that you 67.
Okay, so
Okay, data will be changed 08 AA. Okay, comment out from
Yeah,
164.
164, just like before.
Exactly. That including everything inside definition for that if 67.
Just like that.
Exactly. So that now you can run. Make sure they have to pass that 3 and 4.
Okay, all right. So,
Okay.
yeah, I'll thank you a lot, Sam and Mr. Pham, both of you guys. You've been super. Hey, I'll have to wait till I get to the lab tomorrow.
And
Okay.
then look, and then like you said, go look at the one with the ADC real quick.
Oh, the ADC?
Go scroll through the one ADC definition.
Did I get there yet? Wait a minute, hold on. Let me, 3, 4, 5, 6, and I know you got to get to the in main and it comes after the in main. Okay, yeah, now I'm past in main. And now I want to get to the ADC part. Just a minute.
Okay. Okay, so we're
go-
failing, you're failing when you're reading, correct?
Yeah, please. Test memory ABC. No. I gotta get out. I gotta get to the definition that you want. Yeah, this one you want right here, right, Sam?
Okay, read data. Okay, scroll down just a bit. Okay, so okay, click on read memory data. Right click on read memory on line 398. Right click,
On it.
right click, go to definition.
Go to definition right here, correct?
Go to definition.
Oh, definition, the next one, and click on it.
Yes. Okay, so redefinition. So that looks good. Right to port D, that looks good. Okay, all right, let's go ahead and go back to the test ADC one more time. So you got your definition, that's read is correct. So let me see your definition for your.
Am I too far up? Man, it seems like I'm always past something. Or... No, that can't be. I gotta remember one.
So read there, so read memory, and then you got measured data, read, okay. So that should be there. Okay, so that looks good. Click on your, what your phone, let me see. So we're gonna be writing that should be reading. That should, I don't see anything with the ADC. Like I said, because of that, it's required what you have to do in test 3 and 4. So if 3 and 4, we have to make sure 3 and 4 works first before we deal with the ADC, because it
Yeah,
does meet.
exactly.
Yes,
maybe when he run 3 and 4, they fail
yes.
for the hardware. So you have to fix that before we can go down.
Okay.
Okay, so I better wait till I get to the class tomorrow to put it on a good controller box.
Now we don't care about the control right now. You have to run for your control first to see they pass 3 and 4.
Yeah, I know, but I need a controller box to do that.
Okay, that doesn't matter.
So where do you want me to go right now? What do you want me to do?
Okay, compile your program ready, and you want it tomorrow, you can get a control box from the class and try to run.
Yeah,
Hey, Joe,
yeah.
you said it fell at 21. What about 22, 23? Are they all failing or
It didn't get that far.
what do you mean it didn't get that far? When it failed, if you hit,
Test number 20.
right, once it failed, if you press any key, it should then carry on.
Well, it'll carry on in red, but it won't be, it'll say measured data is this and expected data is that. It'll,
Right. So in other words, everything failed thereafter.
right, yeah. Well, I would assume so. Yeah, the program didn't go on.
No, it gives you the option to press any
Yeah.
key and it'll carry on.
Right, but then if you can keep doing that, but then at the end, it's going to eventually say fail.
Right.
And then, yeah, if that's the case, because you said it fell at like 21, right?
Right.
So if it's 21, you have to check your array, make sure your array is correct, your input array.
Yeah, I know you're talking about, let me go down, so. You're talking
Yeah,
about all
make
this
sure
stuff.
those are, yeah, make sure those are correct. Make sure you look at the word from the Excel, make sure those are,
Okay,
because if you expect it doesn't match up what it is. Then.
okay. Well, in any case, the way it is right now, it compiled, 1 succeeds, 0 fails, so.
Okay.
So Sam, you guys are saying, just come in and work on it tomorrow, correct?
Well, that's the only way that we are available to work.
All right, and thank you for the help that I did get today, right now. Thank you,
Okay.
guys. Thank you, Mr. Pham. Thank you, Sam, and thank you, Michael.
Okay, Sam, run the quiz.
Okay, yes, sir. Okay, go ahead, stop you sharing, Joe.
Okay, yeah.
Okay, so. we're
Like,
gonna
once
be-
again, you guys, thanks a lot.
Okay, here goes quiz 7. Okay, so make sure you download the answer sheet from the website. Okay, let me see. I want to make sure that it doesn't have any answer on it before I run on that. Okay, share screen. Yeah, this one, share.
Sam, you guys are
Okay.
recording this, right?
Yeah,
Okay, so we're gonna be slideshow start. Okay, can you all see?
yeah.
Okay. Okay, so that's pretty much it. Make sure you upload this into the website before 12 noon tomorrow. Okay, let me go ahead and stop sharing. Let's see on the chat what's going on. Okay. All right, look like everybody's good. So anybody have any other question before we go?
I will ask you tomorrow in class.
Okay, yeah, for Tech 2, yeah, if you have lab question, just wait until tomorrow and bring it up and we'll help you there, okay?
Yes.
All right, so that's pretty much it. Back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're
Thank you,
welcome.
Sam the man, Mr. Pham, thank you.
Okay, so anyway, good night, everyone.
Good evening. Bye.
Good night, good night.
Good night.
Good night. Thank you.